Okay, class, this is going to be your 7.3 video. 7.3 is kind of a crash course in all of linear algebra, I guess combined with 7.2. So I do apologize. If you haven't done that, then hopefully in college algebra you did a little bit of row reduction. If not, well, buckle up. So when we're talking about vectors, and I mentioned that they were column vectors here, they're linearly dependent if there is a set of constants so that we can take a linear combination of those vectors and get 0 where not all of the constants is 0. It always works if all the constants is 0, so we just ignore that case. If the only set is the all 0 set, then we say that those vectors are linearly independent. And for instance, the set of vectors 1, 0 and 0, 1 are linearly independent. There's no choice of a constant to multiply by this and a constant to multiply by that to add up and get 0 unless this constant is 0 and that constant is 0. And so that forms a linearly independent set. So here's a less trivial example. Does this set of vectors form a linearly independent set or a linearly dependent set? And if they are linearly dependent, find a relation that shows a non-trivial linear relation. In other words, find the set of constants that works, or some set of constant that works. So we can set up this equation as a constant times each of our vectors equals 0, and then rewriting our vectors as who they are, then we start to get a matrix equation. This is a vector equation, but if we realize that this only happens when we multiply the matrix made up of these vectors by the vector that is made up of our constants, so that last equation on the previous page and this equation are equivalent. Same thing. This is C1 will always get multiplied by the things in the first column, and C2 will get multiplied by the second column, and C3 will get multiplied by the third column. So that is the same equation. This equation has a non-zero solution if and only if the determinant of the matrix is not 0. I'm sorry, has a non-zero solution if and only if it is equal to 0. The determinant is equal to 0. That'll mean that they are linearly dependent. This determinant has to be 0 because the last row is all zeros. So if I don't start my determinant up here, but if I start it down here, it's 0 times that determinant minus 0 times that determinant plus 0 times the last determinant. That's a lot of zeros. So we get that determinant is 0, so those three vectors, 2, 1, 0, 0, 1, 0, and negative 1, 2, 0, form a linearly dependent set of vectors. Now we just have to solve. So we can solve the system, and we're just going to use row operations, Gaussian elimination, row reduction, however you learned the phrase. We're going to put our matrix, we're going to augment it with our right-hand side vector, and we are going to do row operations until we get a solution. We already have a row of zeros at the bottom. We'll start by switching row 1 with row 2, putting a 1 in the top left corner, and then we'll use that 1 to eliminate the 2 on the middle line there. So 2 row 1 negative 2 row 1 plus row 2 will give us 0, negative 2, negative 5, 0. We'll put that in row 2. Then we'll rescale row 2 so that we have a 1 in our pivot position. And then we can use that 1 in our pivot position to eliminate the 1 above. So we'll just subtract row 2 from row 1 and put that in row 1. So then we've put our matrix in reduced echelon form. That's the fancy linear algebra language, but we've row reduced it, right? So then we have a system, and there's lots of different systems that we could pick here, but that's the idea, is we know that from here C3 can be anything we want because it's getting multiplied because the bottom row is all 0. So C3 can be anything we want. C2 plus 5/2 C3 has to be 0. So C2 equals negative 5/2 C3, and C1 minus 1/2 C3 has to be equal to 0. So C1 equals 1/2 C3. So we can come up with a solution vector for our constants that is C3 times 1/2 negative 5/2 1. Any value for C3 can be picked here. If we pick C3 equals 0, it still works, but it doesn't give us a non-trivial set of constants. It would give us all 3 constants for 0. So a nice one is to pick C3 equals 2 to get rid of our fractions. Then we get our vector would be 1, negative 5, 2. And if I take 1 times the first vector minus 5 times the second vector plus 2 times the last vector, we get 2 minus 2 for the top row, 1 minus 5 plus 2 for the middle row, and 0 for the last row, which is the 0 vector. The reason why we want you to be able to find these vectors that these sets of constants that lead to a non-trivial linear relation is because of this idea of eigenvalues and eigenvectors. And if you took linear algebra, and I know 2 of you did, I think is what you told me before, then you'll have seen these, and if not, it's okay. But they are an important method that we use for solving certain differential equations. So an eigenvalue is just a special number. I think that's literally what eigen means, is something like special. It's a special number so that we get a weird solution to this equation where multiplying a vector, a specific vector, by our matrix is the same as multiplying that vector by some constant. And that constant is lambda, the eigenvalue, and that vector is our eigenvector. So they come in pairs, and an eigenvalue doesn't always work, and an eigenvector doesn't always work, but they come in a specific pair so that there is a constant and a vector that when I multiply those together, it's as though I multiplied that same vector by a. And these special values for our matrix are nice, and you can kind of see why, because in certain cases we can replace the matrix with just that number. So here is a quick example. A is the matrix of all ones, and notice that if I multiply it by the vector of all ones, that I get 2, 2, which is the same as 2 times 1, 1. So in that case, lambda would be equal to 2, and our eigenvector would be equal to 1, 1. But it's not the only one that works. A times 1, negative 1 is the same as 1, 1, 1, 1 times 1, negative 1. That's going to give me the vector 0, 0, which is 0 times that eigenvector. So for this eigenvalue. I get an eigenvalue of 0, and I get an eigenvector that goes with that eigenvalue of 1, -1. So lambda equals 2 and lambda equals 0 are eigenvalues of the matrix with corresponding eigenvectors (1, 1) and 1, -1. So here's a question. Does this 2 by 2 matrix have any more eigenvalues? How can we figure out what they are if we don't already know what the eigenvectors are? And so here we have the eigenvalues of an n by n matrix are precisely the solutions to the nth degree polynomial equation in lambda, the determinant of a minus lambda I equals 0. This is called the characteristic equation, and it is a polynomial. Just let me 1, 1, 1, 1. That's A. So A minus lambda I is equal to 1 minus lambda 1, 1, 1 minus lambda. And so the determinant of A minus lambda I is equal to 1 minus lambda squared minus 1. And so that's equal to 1 minus 2 lambda plus lambda squared minus 1. And if I set that equal to 0, I get lambda times lambda minus 2 equals 0. And so from there you can see lambda equals 0 is an eigenvalue and lambda equals 2 is an eigenvalue, and those are the only two I get, and they will be the only two I get because the determinant of A minus lambda I only has lambdas on the main diagonal, so the highest power of lambda you're ever going to see is the size of your matrix. So for a 2 by 2 you're going to get a lambda squared. For a 3 by 3 you're going to get a lambda cubed, and so you're going to get a number of eigenvalues equal to the number of rows in the matrix, except maybe that something might be repeated, right? Because it's the number of solutions to a polynomial equation. So we might have fewer real solutions than that. So it's called the characteristic equation, which shouldn't be new to us. If we can solve something by using a polynomial instead, we've called it a characteristic equation. We've done that 2 different times so far, so this is the 3rd. And so here's what I was just saying. 2 by 2 matrices will have quadratic equations in lambda, so they'll only have 2 eigenvalues. And whoops, we just did that, right? So the determinant of A minus lambda I is the determinant of 1, 1, 1, 1 minus 1, 1, 0, 0 times lambda. This is exactly what we just did. Setting that equal to 0 gives us those eigenvalues we found. So then how, oops, wrong one. How do we get our eigenvectors? So starting with lambda equals 2, to get the eigenvector, we actually take A minus lambda I, and we write that, so that's going to be 1 minus 2, 1. That's going to be 1 and 1 minus 2. And so we're solving A minus lambda I times x equals 0. And why does that work? Well, because that's AX equals lambda I x, which is the same as lambda x. That's the equation we said it needed to solve. So here's my A minus lambda I. I've got it written up here. And we need to solve this. We need to find a solution of this equation that isn't trivial. So we can simplify it. So we get negative 1s on the main diagonal. We can row reduce this because we know that the determinant of this is 0 and it's a 2 by 2. This second row is always going to eliminate. This is easy here, right? We just add row 1 to row 2 and row 2 goes away. So we end up with, if we row reduce this, this was equal to negative 1, 1, 1, negative 1. If we row reduce this, this is negative 1, 1, 0, 0. And so we get that x1 equals x2, and x2 is free or arbitrary. And so an eigenvector that goes with this lambda is x equals 1, 1. That's the one we used earlier. And we can do the same thing when lambda equals 0. So now the determinant of a minus lambda I, that's going to leave everything the same, right? Because lambda is 0, so we just get 1, 1, 1, 1. And when we row reduce this, we get taking row 1 minus row 2 and putting it in row 2. We just get x1 equals negative x2. So a solution for this would be 1, negative 1, or negative 1, 1. They would both work. And so that's how you find the eigenvectors that go with an eigenvalue. All right, that's it for today.